10 o'clock. Okay, Rob 101. 5 weeks down, week 6, working on 4th homework. I mean, we're not at halfway point of the course, but we're moving along. Things are happening. Hopefully matrices and vectors are becoming your friends, and you couldn't live without them now. You would never go back to x1 plus x2 equals 3, etc. So when we opened the course, we did a couple of examples of systems that have unique solutions, they have no solutions, they have an infinite number of solutions. And so now, in this chapter, we're just solving that completely. So let's remember that AX equals B. By writing down the columns of A times the components of X, we figured out that that has a solution if and only if B is a linear combination of the columns of A. And then another way to say that, as we're moving towards a method to have computational attractivity in checking the condition, is that if you look at the matrix A with B appended to it, you should not get more independent columns because B is already a linear combination of A. So this matrix...
Professor, I think you're muted for the Zoom call.
Excuse me? You're muted. Shouldn't be. I'm muted. Okay, I'll check again. I'll disconnect. Definitely not muted in the room.
No, I think it's just a Zoom call.
Okay, let me see. Sorry, people. And I'm happy that you reached out. The host would like you to unmute. Okay. And how's that? Everybody hear me now?
Yep.
All right, thank you for reaching out. That was Richard. Thank you, Richard. We appreciate it. It'd be really bad. Okay, so what I was saying, we started out at the beginning of the semester. We wrote down these equations with 2 and 3 terms. It was really tedious to go through and determine if we had a unique solution, no solution, an infinite number of solutions. We now have the matrix formulation of it, and AX equals B has a solution if and only if B is a linear combination of the columns of A. And another way to say that, because if B is a linear combination of the columns of A, then the number of linearly independent columns here has to be the same as the number of linearly independent columns of A. If you get more, then B is not a combination of the columns of A, and we don't have a solution. Now, this is a little bit cleaner way of writing down the number of linearly independent vectors. So I'll go through it just a second. So we take a set of vectors, and often they come from the columns of a matrix, okay? But it's in general. We can work left to right. We can work center, left, and then right. We can work right to left. You just need to be systematic. Otherwise, you won't check all the possible combinations. But let's just work left to right. Is this a linearly independent set? That's if and only if V1 is not equal to 0. That can be yes. That can be no. If it's yes, throw in V2 and ask if that's linearly independent. If this was the 0 vector, now you move on to V2. If this is yes, then you add in V3. If this was no, then V2 was dependent on V1, and you look at V1, V3, etc. Okay, so you can go through all of these. You can work left to right. You could write a for loop to go through and do all this, but certainly by hand, it's super tedious, and it's doing it with a for loop on a computer is pretty tedious as well. So then we started working towards the following. We have the following statements are equivalent, and this was just before we quit on Friday. We take our vectors to be written down in notation, go back, to be written down just like they were the columns of a matrix, because we're going to throw them into being the columns of a matrix. So if this set V1 to Vm has k linearly independent vectors, then the columns of A has k linearly independent vectors. And the last thing we did for checking that was similar to our pro tip for doing linear independence. Similar, but not exactly the same. is we do A transpose times A, we do its LU factorization, and then the result is U and A have exactly the same number of linearly independent columns. And then because U is triangular, this is a much easier thing to test. It's much easier to go through and solve simultaneous equations if they're triangular. So U is upper triangular. And then where we left off on Friday is kind of with this question. I mean, we're hoping this is true. Suppose U has K linearly independent columns. Is that exactly the same thing as checking just the diagonal of U and looking at non-zero elements on the diagonal? Okay? That's kind of where we left off. Is this true? So is there something better than doing linear independence? Can we just count non-zero elements on a diagonal? Okay, so here's the answer. And the answer is almost true. Okay, so what does almost true mean? Okay, it's almost true. So it's true under some easy conditions to verify. So it's yes if, and I'll write it kind of in a Julia type way. So that's a diagonal element of U, right? Okay, if this equals 0, implies the entire row is 0. So there's the entire row equals the 0 vector, okay? So entire row. Now in Julia, that would return a column, but I just don't care, okay? It's just a vector. It's a 0 vector, so that's the entire row. So it's yes if that condition holds, and it's yes if diagonal of U has 1 or no zeros. If it has 2 or more, then you have to check the rows. Come on. You don't want to erase. Okay. Really? Ah, gotcha. And just to be clear, if diagonal of U has 2 or more zeros, we must check the rows. The row condition above. Okay, so this is super important. I'll put a little box around it. And we'll do lots of examples to make it clear. So it's almost true. That's what I mean by almost, okay? No zeros, fine. Everything's linearly independent. We already know that. If there's 1 0, they're linearly dependent. And in fact, there are then, if they're m columns, they're m minus 1 linearly independent vectors. But if there's 2, something can happen. And I'll show you a counterexample of how that plays out. So I'm going to call this next thing paste in our semi-pro tip. It's in the book, so bingo. I guess that must be it. Okay, so it's essentially what we just wrote down. Okay, but it's in the book and it's in red, semi-pro. It's not the pro tip because it's not as beautiful as it can be. There's another form of LU factorization where you can remove the doubt. But hey, in our first introduction to LU, you guys have done amazing to hold things together this far. Okay, so this says the same thing as before. If the diagonal view has no zero elements, then everything is linearly independent. If it has one zero element, then we have k equals m minus 1 linearly independent vectors. And if it has two or more, then additional computations are necessary, and we look at the rows. Okay, so it's just another way of stating this, which now that you're Julia programmers, you probably like that better, okay? Check the diagonal and then check the rows. So here's an example, and we weren't going to write it out just because there's too many numbers here. So this is straight from the book. So here's a matrix that has 7 rows and 5 columns. You'd never want to do it by hand, right? Just forget it, okay? Just don't even think about it, and you don't even want to write it down in your notebook, all of those numbers, okay? So I created the matrix, and then there's commands in Julia to generate LaTeX code automatically that I can even paste it into the thing. I didn't have to type it out because I created this with a different method. I used some random stuff and some rounding. So I follow our semi-pro tip, and I do the LU factorization of A transpose A. I look at the diagonal, and there's only one zero element. So I know immediately there are then 5 minus 1, which is 1, 2, 3, 4 linearly independent vectors in that matrix, okay? So right here, we can conclude 4 linearly independent vectors. Cool. Now, we did not have to look at the rows because when there's one, you don't need to bother doing it, okay? But I just showed it anyway. We don't need to do that. We do not need to check the rows because there's only one. Hey, don't do that to me. Go back, stay. 1 0 element. Okay, here's one. 7 rows and 6 columns. So we form A transpose A. We stick it in to Julia's LU factorization. This time we look at the diagonal of U, and there are 2 elements. So we don't know by just looking at the diagonal. You need to do the additional test. There's all of you. And yeah, they're not identically 0. There's a 10 to the minus 12 and 13 and stuff like that. You guys are used to looking at matrices now and seeing 1e, blah, blah, blah. Okay, where that exponent is really small. Okay, so because diagonal view has more than 1 0, we had to check the rows. But in this example, from the row test, conclusion, we have 1, 2, 3, 4 linearly independent vectors. Questions? Please.
So what's the row test? Like, how did you get the form?
How would you extract the rows in Julia, or?
So like, we got like, we had 2 zeros in the diagonal, so how is it just n minus the elements of the diagonal minus?
Yeah, so the question, okay, so I think the question is the following. Let's make sure. So we have 1, 2, 3, 4 non-zero elements. We would like to be able to conclude that there are 4 linearly independent vectors. We'd like to do that. We go here and we say, oh, it's not necessarily true, because if we ended up with one of these numbers being, well, it's lower triangular, so it would have to be, say, this number being 2, then we would not have 2 rows of zeros, and then this test would not be correct. And we'd have to go back and then look at the columns of U. That's always true. It's always true that the number of linearly independent columns of U is the same as the linear independent columns of A. And checking for linear combinations that add up to 0 is much easier because this is a triangular matrix. So you've already won, but now we're greedy. We want the really simple, super clean test. All we want to do is count the number of non-zero entries. But this is a flag that we should then print out in Julia, those last 2 rows. So does that answer the question? Cool. Question from, doesn't U mean the whole diagonal elements are 0? That's on there, so. Yeah, so I'm going to do an example. I'm going to do an example where the diagonal element is 0, but the entire row is not 0. Okay, so we will see that you do have to do the test. Okay? Yeah. Okay. So here's the counter example. There's our examples. So here's the counter example. It's really bizarre. And this will not be on any quiz or anything, okay? Okay, so it's a counter examples are almost like proofs, okay? So why are things true, not true, etc. So here's our matrix, A. It took me a while to find it, but it's as simple as can be. Here's A. It's all zeros with a 1 in the middle. So it's on the diagonal. So what is the number of linearly independent columns of A? How many independent columns do you see there? Well, if you work from left to right, that's the 0 vector. You throw it away, right? So then you look at this one. That's non-zero, so that's linearly independent. And then I throw in the 0 vector. That's dependent. So I only have 1. I have 1 linearly independent column. So that's 1. Okay, it's the second column. I'll let you mentally compute the transpose and see that you get A back. Okay. And if you multiply A transpose times A, you also get A back. So it's a really bizarre example, but you know, it's a matrix that you could put into our test, okay? So this is what it means. Is it true always, or is it just true most of the time? And the difference is important. So I'm going to propose an LU factorization. Okay, so Here is a valid LU factorization. And just like we've been doing, because in general you need that row, so I'll make sure we're using row permutations. So here's my permutation matrix. It's 0, 1, 0, 1, 0, 0, 0, 0, 1. Okay, so what does this permutation do? I've swapped two rows of the identity. So what does it do when I multiply it times a matrix? It swaps the corresponding rows in the matrix, okay? So this swaps first two rows, okay? So conclusion, P times A, well, it swaps the rows. So the middle row of A is 0, 1, 0, and the top row is 0, 0, and it leaves the bottom row unchanged. Ooh. Okay. I'll write this in red. Now we want P times A to equal L times U, where this is lower uni triangular, and this is upper triangular. There we go. It's sort of in there. Close enough. Okay, well, this is what I'm going to do. I'm going to take L to be the 3 by 3 identity matrix. And I'll take U to then be 0, 1, 0, 0, 0, 0, 0, 0, 0. Okay, so then it's clear that P dot A is equal to L times U. L is the identity matrix. Okay, so how many elements are 0 on the diagonal of U? Okay, so the diagonal of U that's 0, 0, 0. Okay. But I do not have 3 rows of 0, okay? So our simplified test fails. Okay, so it's not true that I have no linearly independent column, because diagonal of U has no non-zero elements. U has one linearly independent column, just like A does. Okay, so here's A, it has one linearly independent column. U has one linearly independent column. Is this linearly independent? No. Is this? Yes, we have one. We add this to it, does it stay linearly independent? No, so one linearly independent column. Whoops. Just like A, just like it's advertised to, one linearly independent column. Okay, so let me go back to our statement. Is it true that if U has k linearly independent columns, that is equivalent to diagonal of U having k non-zero elements? And the answer is no, it's not true, okay? It is true if U has one or fewer zeros on its diagonal, and it is true if whenever you find a zero on the diagonal, you look at the entire row and you get zero, then everything is fine. And then we go to our counter example here. Here is the diagonal, but this row is not zero. Oh, come on. Be nice to me. Do what I want you to do, not what I tell you to do. Okay, so that's where that fails. Question, yes?
So what does it mean to have only one linearly independent column?
Well, we have only one linearly independent column. We'll see eventually. We know then if we were looking at AX equals 0, we would not have a unique solution. Okay, so the number of linearly independent columns needs to be equal to the size of your, all the columns need to be linearly independent if you want the equation AX equals B, for example, to have unique solutions. And so we don't have as many columns linearly independent. So that's what is important there. And so here we're just showing how do you count in general the number of linearly independent columns. And mostly you can do it by looking at diagonal of U, but not completely. Okay. So let's do a test now. For existence of solutions to AX equals B. So step one, we do LU for A transpose A. And we'll write that as P A transpose A equals L times U. And then we do LU for the extended matrix where we add the columns of B to it. So I'll write that as P extended, AE extended transpose, AE equals L for the extended matrix and U for the extended matrix. Then AX equals B has a solution if and only if U and UE have the same number of linearly independent columns. Okay, so we're counting the number of linearly independent columns. And then, as we just finished discussing, as previously discussed, so we look at diagonal of U, diagonal of UE, and if necessary, meaning we have more than 1 0 on one of those, we look at the rows of U and UE. Okay, so it's not too bad. Not too bad at all. So we want the matrix A and the matrix A with B added as an extra column to have the same number of linearly independent columns, and we do that with LU factorization of A and AE, where AE is A space B. Okay, so we'll do a big example. Let's see, example. Does it have a solution? Bingo. Okay, this one actually isn't all that big. We're going to do big on the existence and uniqueness. Okay, so here's AX equals B, so it's still maybe bigger than we'd want to do by hand. So A is 4 by 3, 4 rows and 3 columns. We want to ask, does it have a solution? So I do the LU factorization in Julia for A transpose A, and I do it for the extended matrix where I add B to that. In this case, look what I get. So diagonal U has no zeros. So all 3 columns are linearly independent. Okay? And then I throw in B, and I pick up 1 0. And if I'm hoping for a solution, that's good, because now I have 3 non-zero elements on the diagonal of AB, 3 in U. Okay, so now I can conclude B is a linear combination of the columns of A. I added B, I did not get additional independent vectors. That's the key thing. Okay, so checking. Once again, going back to the definition of how we would check that. There, go for it, okay? I'll race you. I get Julia, you get Julia. You do it this way, and I'll just do LU factorizations, and I'll solve 10 problems before you even get your first one solved, okay? So that's the power of having analytical tools, guys, okay? So we're just trying to count the number of linearly independent vectors, and that allows us to do it. So conclusion, there does exist a solution. Okay. Now, let's check for existence and uniqueness. Okay, so if we have AX equals B, okay. Okay, so here, A can be n by m, and then B is n by 1. X is now m by 1. So A times X is n by 1. Okay, so we don't care if it's rectangular, square, anything, guys. So what's the easiest thing to check first? We're looking for existence and uniqueness. What's the easiest thing to check? How about in the chat? Can you guys beat them? If I want to check uniqueness, what do I need to do? Uniqueness, I need the columns of A linearly independent, but that's determinant A transpose A not equal to 0. That means if I were to do the LU factorization of A transpose A, how many zeros are on the diagonal? 0, okay? So, uniqueness. So just check that first. You need it anyway for the existence because you have to compare the number of linearly independent columns. So if you want to know existence and uniqueness, if it's not unique, you can just stop. Say, nope, okay? Uniqueness, we look at, so that's columns of A linearly independent, and that's if and only if determinant of A transpose A is not equal to 0, and that's if and only if I do my beautiful LU factorization, and I do it anyway because if A transpose A is 9 by 9, that's the only way I know to get the determinant in a numerically copacetic manner, okay? So that's if and only if diagonal of U has no 0 entries. Okay, we don't know if a solution exists, but if it does exist, there's only one of them. Okay, so now let's do the existence part, and you'll see how all these tests just fit together like a glove. Existence, we need B is a linear combination of columns of A, and then that's if and only if now when I do my PE times, here, I'll write out A space B transpose A space B equals LE UE. That's if and only if U, oops, I didn't want that big one, and UE have the same number of linearly independent columns. Okay, so let's put it together. We want existence and uniqueness. How many zeros are on the diagonal of U for existence? And the answer is none. So if we already know that we have uniqueness, and now we're checking existence, how many zeros do we want on the diagonal of UE? Sorry, 1. Because we want B to be a linear combination of the columns of A. And so our test, we don't have to look at any rows, we don't have to do anything, okay? It's just looking at the diagonals of U. So if we have determinant of A transpose A not equal to 0, then uniqueness, existence becomes diagonal of UE has 1 0 element. Yay. Okay, so that's super cool. All the crazy row stuff. If we're really only concerned about existence and uniqueness, the first one, there's no 0 elements. That's determinant of A is not equal to 0 because the product of the elements on the diagonal of U is proportional to the determinant of A. Okay, so that needs to be non-zero, and that means no 0 elements. And so once we have that, then U and UE have the same number of linearly independent columns, if and only if when we add B to A, we don't pick up another independent one, so we need a dependent column, so we need 1 0. We need 1 0 element on diagonal of UE. Okay, so let's do some examples of that and see how that works out. Bingo. Existence uniqueness, part A. Bingo. Yay. So this is in the book. You can put it in your notes. And typo, 2 typos, not get right. So here's an example that most of us, if we did it by hand, there's no way we would get it right, okay? Is there a solution to this thing, and is it unique? Okay, so this is the harder case because we form A transpose A, and there's a 0. So we conclude if a solution exists, it is not unique because the columns of A are not linearly independent, okay? So conclude. Columns of A are not linearly independent, and hence, if a solution exists, so now if the question you are posing yourself, does there exist a unique solution to this system? The answer is no. And if that's all you want to know, you stop here, okay? You just stop. So checking the independence of the columns of A is always the first thing to do. So you need that. Now, this is mostly just to be pedantic, okay? We go ahead and check existence. Okay, it's not that interesting probably, but if there is a solution, then there's infinite number of them. Whoops, I want to insert something. So insert image file, and it's big. File, big. Part B. Out of the way. So to check existence, we append the columns of B to A, and we do that LU factorization. And this time we get 2 zeros. So there's a chance that a solution exists. Okay, we did not add to the number of linearly independent columns potentially. And we confirm that by checking the corresponding rows. They're identically 0. So our test is 1, 2, 3, 4 linearly independent columns of AB. And we go back and look. 1, 2, 3, 4 linearly independent columns in A. Hence, B is a linear combination of the columns of A. And hence, the solution does exist. Conclusion, solution does exist, but is not unique. Okay, and we can do that at scale. That's the point, okay? We can do this at scale. We're not stuck with little 2 equations and 3 unknowns, 4 equations, 4 unknowns, things like that. We can do this at scale. So probably we'll have to start Wednesday like this, but there's a question on Julia homework 4. That's what they're working on, yeah? Or is it 5? Maybe it's 5, yeah. So this is for Julia homework 5. I guess they always go with a little j. So. How do you actually compute AX equals 0, x not equal to the 0 vector? When the columns of A are linearly dependent. Ooh. Okay, so can you do that at scale as well? So if you want to find a linear combination that gives you 0, how do you do it? How do you do it? Okay, that's the last thing in the chapter, and then we're going to move on to one of the superpowers of linear algebra, which is regression, fitting models to data. And it'll be something you'll use over and over and over in your physics courses, engineering courses, and nobody else in your courses will know how to do it except the Rob 101 students, and you'll blow everybody away, okay? So regression is coming up. It's really, really cool. Thank you. I've used up my time. I'm a minute over, and I'll be on office hours in half an hour.